Hello, everyone. I'm Mark Trugenti, the Director of Design and Engineering for Burt Process Equipment. Welcome to our first educational webinar of 2024. Today, we're going to be talking about ChemPlus and PolymerPlus units. We're going to kind of delve into some of the technology that's involved with them, look at a few case studies, discuss some of the options, how they're designed. Um, uh, Throughout the presentation, we will be posing a couple of poll questions for those who are interested. And Catherine Diaz is joining me today. Catherine is one of our other engineers, and she'll be assisting me with questions. I like to keep these kind of open. If you have any questions as we go along, please feel free to type them into the chat window, and we'll try to address them on air. There'll also be time at the end of the presentation for any questions. And following this, we'll be sending out a survey. And we always are interested in your feedback on topics, what you liked, what you didn't like, and things you'd like to see in the future. So as always, thank you for joining us today. And let's kind of get into it. What we're going to do today is we're going to talk about two related types of systems, the chemical feed system and the polymer feed systems. And they go hand in hand because they are based on some similar technologies, but really because they're used sort of in conjunction. In a lot of ways, a polymer system is sort of a specialized version of, the very broad topic, which is obviously chemical feed. So today we're not going to be able to cover everything related to chemical feed. We're going to kind of talk about it, kind of a broad basis. There's a lot of different pump technologies, a lot of different chemicals, a lot of different applications where chem feed is utilized. We're going to highlight some of the ones some of the ones you'll encounter, some of the more prominent ones you see, in different engineering applications. So I'm Mark Trugenti. I'm the Director of Design Engineering and Business Development for Burt Process. I'm a chemical engineer by trade, so feel free to get as much into the chemistry as anybody wants to here. I won't go too deep myself, but if we have any questions, we can certainly kind of take a deep dive. I've been with Burt Process for almost 18 years at this point, working with numerous clients around the country on a lot of these different types of applications. So what is a polymer system? I guess the big thing we need to answer first is, what is a polymer? I'm sure everybody's heard of the term polymer, plastics, but polymers are long chain molecules that act like magnets. So kind of think about it like a long string of spaghetti, essentially. And on that, unlike most chemicals, you may see, acids, bases, we have a single ionic structure. Polymers are basically these chained organic molecules, and on them they have all of these different basically active sites, whether they're ionic or they're cationic, positive or negative, or they're neutrally charged. And the reason that really what a polymer does is a polymer is added into a stream to essentially bond to certain constituents of that stream. And by doing so, it adds mass to it. That's really what you're trying to do. You're trying to use the polymer, which in some ways almost kind of think about it, almost kind of sort of like a thick, almost like oily substance, and it basically bonds and then allows whatever target you have in the waste to basically be bonded to these different sites. Because of the nature of polymers are kind of fragile. I mean, they are chemically bonded. They're also activate in water. So once they're immediately exposed to water, they tend to open up. They tend to grab onto molecules. So very often they are shipped they're basically shipped in an oil or in some kind of an emulsified form, basically bound up. So think about, if you cook your spaghetti in the pot, you put it in the colander. Now you have this giant ball, basically, of different strands that's basically encased in there to basically then allow for proper shipment and then use. So polymers need to be activated before they can actually be utilized in the system. And you do that by basically unraveling your ball of spaghetti at this point. So there really are kind of two different ways. There really are three different outcomes when you activate a polymer. I'll talk about what polymer activation is here in a second. If you insufficiently mix it, so if you don't separate those spaghetti strands enough, you really don't have enough activation sites. You're only utilizing part of the polymer, and ultimately you're just wasting chemical at that point. Your strands are still intertwined with each other, and it's just not a very efficient usage. If you overexpose it, if you basically overactivate or try to pull it apart too much, you just break the strands. And at that point, at that rate, you basically, again, you're forced to overdose, and you just basically lose the efficiency. What you really want to do is take that, basically take that nice ball of spaghetti and basically stretch it out in such a way that now I basically have these beautiful long strings, all of which that can individually bond across different ionic sites for what I'm trying to add into the system. So polymer activation is done in a couple of different. Is really kind of like a two-step process. One, I want to basically strip away whatever oil or emulsification is protecting the polymer, and then I also want to get it to basically open up. So when I immediately expose it to the water I'm trying to trying to put it in, I have this now fully active, an energy efficient polymer. Um, as soon as that polymer, which is obviously an organic chemical, hits the water, it basically opens up at that point. So there's a couple of different ways that you can do this, but the most efficient is really what's referred to as a motorless activation system. So a lot of people traditionally think of polymers, they think of chemicals, they think of mechanical agitation, where you're basically putting energy into this. So it isn't so much a feature of physically mixing it, like you're thinking about mixing like a chemical into a drum. It's a question of basically putting energy into it at that point. So you can do this by basically applying it to, having like a mechanical agitation. The other method of doing it, which is what I generally recommend, is more of a hydrodynamic polymer activation, which is when you increase the velocity of the polymer. And by increasing the velocity of it, you're putting this high level of energy and effectively stripping that oil, and then activating the polymer for high use. You can kind of see it here in a couple of different examples. So this kind of shows, sort of what it looks like when you have basically like a high velocity, and you're accelerating this to like 70 feet per second, 40 to 70 feet per second when you're doing this. The polymer and the water come in, they're then basically accelerated. I'm just gonna skip to the next slide. I like this one better. Here. Oh, there we go. Makes a lot more sense if you look at it as an animation. So what you're looking at here is you can basically see the polymer in green here, basically being injected into the molecules that are blue. And as you're doing this, you're basically just accelerating them at that point. You're not actually physically mixing them. You're basically going into this, it's basically going against that spring under the actual pressure of water, and you're basically accelerating it, going to like a venturi that basically accelerates this now to a high degree, which then fully activates the polymer. That's really what we're showing here as animation. And this is one of the more efficient ways of doing polymer activation. There are other ones, and they're also what we refer to as dual action or dual step polymer activation, where you're doing something like this and then also going into more of a mechanical mixing device. So this is what's referred to as dual activation. And again, the reason why, and again, there's not enough time today to go into a real deep dive on all of this. It is very polymer specific ultimately. Um, when you're doing polymer activation, different polymers, different concentrations of polymers, that is also what sets in motion what you want to do as far as activation. Doing more of a hydrodynamic or basically, acceleratory polymer activation is good in a lot of cases, but depending on the nature of the polymers that you're utilizing, and that's really determined by chemical testing. You take a sample of your water, work with a chemical company, they'll kind of look at this, look at the different polymer options that they have or that others have, and you can really see what the actual best test results are. You may need to have different levels of activation in them. In a dual activating system, you're going through that hydrodynamic activation first, where you're using that acceleration, and then you're going into basically a low shear mixing chamber like this to allow for then further activation into the system. Polymer usage really does vary depending on what you're using. Obviously, so there's a lot of polymer can go like a long way. In probably one of the most common situations people actually see polymers is when they're looking in a swimming pool. If you ever put like coagulants into a pool, for example, you put it in, it mixes, and it basically takes everything out. If you overdose or underdose polymers, you can end up with a real situation. Underdosing a polymer, it doesn't have any effectiveness. If you put too much into your system, you can then end up where you basically have this sort of like amorphous glob, basically a polymer in there that's really just bonding to itself, bonding to itself. So it is important to understand how much dosage you have. And in a lot of ways, polymers, unlike a lot of the chemicals, are used in smaller quantities. You can see 0.1 up to 500 gallons a day. And 500 gallons a day is a lot. We're talking about municipal treatment, we're talking about very large volumes. There's a lot of polymer goes a very like a long way, when doing this. And this is just one example here of a metering pump style system. Where you come in. This is kind of what they look like, effectively. You have your water inlet coming in here, you have your chemical feed here. This is your activation chamber, and this is your activated solution then coming out of your system. Polymers are always blended with that water at the point of actual activation. Before I go further, I think we have our first poll question.
Yes, we have a question here. What do you offer for electrical controls, full panels, motor protection, or junction boxes?
Of course. So, when looking at these type of systems, we talked a lot about polymers, the actual activation portion, but that's actually just one part of a much larger overall system. You still need to have all that controls that then go into the chemical injection, that they then go into the actual water flow control. So there's a lot of different options, and depending on what kind of application, it's going to be standalone kind of units, where they're going to have like their own basically PLC, or in some cases still today relay-based controls, or these will tie into a full SCADA base or other kind of full automation system as part of an overall municipal system, where it's tying into storage tanks that hold the polymers and other types of chemistry, other types of systems as well. So there is a lot of diversity in what can be done with these. This one here, for example, shows a full PLC system, but there are also other ones as well. Yeah, another type of pump is what's referred to as a progressive cavity, and here you can kind of see like on a 3D animation, like a 3D view of what more of a dual activation system is. Progressive cavity pumps, and what you also want to do is you want to have a pumping technology for your polymer that obviously does not damage it. So that's one of the reasons you do see progressive cavity, and other types of peristaltic pumps where you don't have that energy or that kind of a shear, where you're going to have like centrifugal style designs you're going to end up putting in or actually damaging your polymer system. Just a few other kind of types of features that can go into these systems, increased dilution water, flow switches, polymer flow meters, explosion-proof designs, customized system designs, age and blending chambers. We'll talk about that in a few minutes. We'll talk also about some of the solid feeders, um, proportional, different types of metering pump technology, very high flow systems, as well. And really, this can be designed also with redundancy as well to help meet different needs. There can be simplex. We've looked mostly at simplex style systems. There are also our duplex designs as well, which can be utilized for these types of systems. I think here's the time for our first poll question. Again, these are totally optional. If anybody wants to take a look at them and kind of just ask a couple of questions about what we've been talking about here to see, kind of what your guys' feedback is, as far as these polymer systems are concerned. All right. So when you're talking about, obviously the poll question was, what is it related to do with the different types of polymer systems? And the answer is obviously you're looking at ones that put the highest velocity into them, which I believe is answer C. And again, that kind of example is really, building up the rest of the polymer system. If you don't have the right polymer activation going on in your system is going to have issues. Either you're going to use too much polymer, or you're not going to get the right results with it. So really, we can talk about different pumping technology. We can talk about redundancy, like we see here. This clarifier application, again, most time polymers are used to add mass to a system. Double containment, for example, is a different option, which you can see here. But if you don't have the right amount of, you don't have the right type of activation going on in your system, um, you're already kind of starting off, obviously, on the wrong foot with these types of systems. We've talked predominantly today here about like liquid-based systems. And while liquid is common as an engineer, I typically recommend people use liquid systems. There are also dry polymer-based systems as well. And they operate very differently than a liquid-based system because obviously you're starting with a dry polymer design. So it's less about that activation and it's more about at this point you're taking your polymer and you're effectively blending it and aging it in water prior to use. And this is typically done, your polymers come in either granular, flakes, or beads. And because it's not, basically that ball of spaghetti, but it's basically, with the raw pasta I'm putting in, it's not so much of an activation as kind of a more about cooking it at that point, and sort of use spaghetti analogy again there, and then basically using it right out of the water at that point. So, what you're really trying to do in these type of systems is not activate them, but you're trying to hydrate them effectively prior to use. And you can kind of see one here where you have like more of a hopper-based design. There's a few different ways that these work. So there is these which are more like a solid feed system, or like coming out of a hopper. You're basically feeding these into a water-based system that goes through like an inductor design, and then these typically also are then going to some kind of a blending tank at that point. There's also like an auger base where you have like a higher flow at that point, and you're basically feeding it into a tank. You can see here a couple of different designs. One of the issues with dry polymers is moisture outside of the tank. So when you're utilizing them, you have to make sure that whatever you're actually feeding from, whether it's a super sack or an auger, or more of a like a hopper-based design, that you don't have atmospheric moisture or water in the plants that then causes to start to basically starts to basically dissolve it at that point, because now you end up basically with this brick that you then have to try to design. It's going to begin to actually bond to itself. Is the more high efficiency. They also do, and you can see in this case here, these are more like actual, almost more like a suction style design, which I think I have here, where you can see where they basically just suck these in basically with what they call a disc feed system at that point, where you put the dry polymer on more from a hopper, which is then basically using air, basically sucked into and then goes into that vacuum inductor at that point for dispersion into water. So obviously these schematics look a little bit different than some of the other ones we've looked at before. And that's because now you're talking more about aging, in blending tanks. And while you could do this with liquid polymers, this is very common where you're talking about, dry polymer systems. But aging is basically a feature whereby after you basically allow the polymer to be activated or dissolved into the liquid, then you give it an X amount of time to then basically increase its efficiency. And again, it's a little bit of a polymer specific about whether or not you want to do that or how long you want to do that. But here's kind of two different designs. One is a dry hopper based system over here, where you're basically drawing out, going through that kind of polymer inductor at that point into an age tank, which then allows that then dry polymer to then be fully hydrated and then goes into an actual pump tank then for actual use. This is kind of a similar design here, mixing section into an aging, and then you have a pump section there as well.
Hey, Mark, we have a question here.
Yeah.
How long have you been using the vacuum disc method technology?
I'd say that technology's been around for at least 10 or 15 years. I don't say it's the most common, to be honest with you. I think most people still go through hoppers more than the vacuum disc style, but I have seen people utilizing it. But I think it's been around. Personally, I think the first one I ever did with them goes back at least about 10 years or so. Sort of switching gears a little bit. Polymer feed is obviously a bit of a subsection of a much broader category of chemical feed, which is basically, where we encompass all the other chemicals that we utilize in a system, whether that's, injecting a polymer, whether it's injecting acids, bases, hydrophlocylic acid, hypochlorites. Really, the list goes on and on of different types of chemicals, which are then metered and controlled into some kind of either a reservoir, pipe, or injection, municipal, different, all kinds of different applications. You can see a lot of kind of images here. We're going to kind of walk through the little more broad sort of subsection now that we've talked about polymer activation of just more generically on chemical plus more chemical feed style systems. So this is kind of the basics of a chemical feed system. I have some kind of a chemical container, whether that's a tow, a drum, a tank. You have a metering pump, you have additional components, back pressure, anti-siphon, pressure relief. We'll go through all those here. A couple minutes, pulsation dampener, calibration column is a little bit of an antiquated thing designed to allow you to do flow measurements for the system. And you're putting this into some kind of a point. And these are used in a wide variety of applications: municipal water disinfection, pH adjustment, fluoride addition, wastewater, food and beverage like clean in place, institutional cooling tower injection, boiler water treatment. Really, in a wide variety of chemicals utilized. And understanding what the chemical is you're pumping, the volume that you need to pump, as well as the amount of redundancies you need in your system, like how critical is the application, simplex, duplex, triplex design, it can never be shut down. And then obviously really finding the ideal sort of pumping solution for that is really what defines chemical feed. You can see here one example. These are large motor-driven metering pumps. This is all PVDF piping, a more corrosion-resistant design than say PVC or CPVC. But that's really a lot of that is all chemical driven at that point. So this is kind of a standard chem feed style system. You can see here the pressure gauges, the metering pumps, the feed lines, different selectable pump options at that point, pressure relief. It kind of went through a few different configurations. You have kind of a more of a stand mounted design here on the left. On the right side, you have a little bit more of like, like sort of like a just like a leak containment style system. So most of these and you are done with different types of technology. You can see here this is actually an explosion-proof style metering pump as well. The standard cam feed units that we utilize are usually constructed on some kind of a polyethylene constructed base. They have different Schedule 80 piping for thermoplastics, or SDR11 or SDR17 for PVDF, polypropylene PVDF respectively. There's also stainless steel options, Hastelloy or other exotic alloys, depending on what the chemical that's being pumped is. You typically have some kind of a containment for the actual pump itself. And then you typically have some kind of a flow verification device, whether that's a smart pumping technology, which we can talk about a little bit, or more of a calibration-based design.
We have another question here.
Yes.
Do you offer anything for splash spray protection? Would we get a leak on the skid?
That's a really good question because one of the things that comes up with a lot of obviously you're pumping a chemical at this point. So in a lot of applications, depending on what the nature of the chemical is, it could be a contact hazard, it could be a splash hazard. There are options for double containment, although within the actual chemical feed system itself, that can be a little tricky given the amount of different componentry involved. So very often these are built with basically like a splash guard protection. You can kind of see here on the right, these sort of like sliding door designs are often utilized. That allows you, because you have to kind of balance that access to the actual system versus personal safety at that point. Um, there are also a few other ones. Um, you have different style doors, more like a hinge design for bigger applications. You can see here, these can also be a lockable design potentially to allow for access. So yeah, these can be Lexan, these can be different materials. We'll see a few later, which are actually cabinet-based designs, which are also done for a means of, there, for example, if you're dealing with more of a hazardous chemical, like a solvent, for example, that also kind of largely sort of comes into play. So there's a lot of different ways, but yes, obviously one of the things, most important things here is also safety at that point when it comes to these types of systems. And double and splash containment particularly is also one of them. So I mentioned before, there are some fundamental, commonalities when it comes to chemical feed systems between pulsation dampers, back pressure, calibration columns, the actual type of pump that you want to utilize in your system. And um, there's a lot of different types of pumps. There are metering pumps, which there are solenoid driven, there are motor driven, there are different peristaltic, different hose pumps, depending on what the flow rate is and the chemical. If degassing is a concern in the system, where you're doing like a hypochlorite, for example, things like an off gas, different types of pumping technologies can get that kind of gas lock in them. So there are better pumps than others that have like a degassing technology. For larger flows, even air-operated diaphragm pumps. If you're pumping it, depending on what the viscosity or the thickness of your chemical is, there's also things like those also can be like progressive cavity pumps, like we saw with the Polymer design. But so there's a lot of the pumping technology is really kind of like what drives this, and that's very chemical dependent and flow dependent. But these kind of features here are fairly common. Pressure relief valves prevent overpressurizing of the pumping system. Pressure relief options, basically to allow you to basically to go back to the pump or go back to the pump suction. These are also utilized a lot when you're trying to prime, for example, trying to prime a metering pump in those cases. Back pressure increases the repeatability. Since a lot of these are peristaltic, whether they're metering pumps or hose pumps or some kind of an AOD pump, putting back pressure on there allows you to basically improve the repeatability. It prevents siphoning when the suction head exceeds the discharge head. You don't actually be drawing back or siphoning in your system. So, um, the ejection flow can create a venturi in the pipe, developing vacuum is control the chemical through the system, even the pump stops. So that's why you really want to have that sort of back pressure at that point. That's really what siphoning is. It prevents basically the vacuum from causing the chemical to be drawn even when the pump is not in operation at that point. You know, these more reasons for back pressure. Back pressure is very commonly put on these types of systems. It also depends on how these pumps are obviously run at different points. So, um, if you do have, different suction points compared to your pumping points, it also prevents basically the transfer of flow in those situations. Some smaller pumps actually have multifunction valves on them, which basically incorporate a lot of these different things between back pressure, anti-siphon pressure relief, and priming. That's only really common on smaller metering pumps. They're not common on all pumps, like hose pumps, things like that. Don't have those types of features readily available. Um, Pulsation dampeners is one sometimes people like to have. If you have a reciprocating pumping system, which is common if you have, again, peristaltic style pumps. Um, what this basically does is you're going to get sort of pressure spikes because obviously it moves fluid when you're actually pulsing whatever that is, whether it's a diaphragm, or the hose. Having a pulsation dampener basically smooths that out in your system. And it basically compresses, so it allows for also allows for much smoother flow in your piping system to your actual chemical point of use. And calibration counts, I mentioned this before, these are really designed to give you some kind of a flow verification of what you're getting out of your system. I see them actually less more and more. Obviously, there's been a lot of improvements in pumping technology that have kind of come into play. And as you've seen that you're seeing smarter metering pumps and more instrumentation that's actually designed to give you real-time pump feedback. So I kind of see calibration comps as a little bit of kind of a throwback, although people still do utilize them. You're seeing it more and more in the digital world where you're going to see basically just smarter pumps. They're going to have leak sensors, they're going to be at the ability to determine some level of flow rate digitally, whether doing stroke counting or revolutions, to basically give you a more accurate reading, simply using a calibration column in most situations. Not integrally part of the actual system, but obviously at your point of use, you may have an injection valve. Um, and what this has done, rather than just having basically just a valve in here, your injection valve allows you to get proper mixing when you're injecting into a pressurized line with your chemical. And here you can see an example of a couple of like hose style pumps design as opposed to metering pump designs.
Another question here.
Yeah,
Can these go outside? If so, do I need any protection?
that's a really, really, really good question. So the answer is yes, you generally do need protection. These types of systems are utilized in a lot of different environments. And depending on what you're pumping, what your nature of your chemical is probably not something that you want to inherently be exposed to the elements. With the classic example, say like sodium hydroxide, if it gets below 55 degrees into the consistency of jelly at that point. Um, so you do need to have some level of protection in these systems. And there's a number of different optional ways to do that. You can simply heat trace the entire chemical system. I think that's not an ideal situation because you do need to have proper access to them. So what we've done, this is just one example here, in sort of more of a customized systems, actually put these in like modular buildings, where you can have a lot of different safety features for these systems. You can see you actually have drainage below. You have a chemical safety showers can be placed like directly outside, with your controls, with acid resistant or chemical resistant lighting, with proper ventilation, HVAC control. And now you're basically creating almost like a containerized system for use, with a chemical feed style system. You can also do cabinet-based designs. This is also really common when you're talking about hazardous chemicals, where you now have to worry about NFPA ratings. If there's going to be potentially fire issues, if you have to do special kind of venting with these systems. So, for example, here you have like vacuum and flame arresters to prevent oxygen from getting in there as well. If it's, for example, if it's more of like a hazardous or solvent-based chemical. You see a lot of this more in like semiconductor production, which is obviously ramping up battery production facilities. You see a lot more usage of technology like this. Um, and the other issue being outside could potentially be that now you need to move into the world of having like hazardous location systems, whereby now you have explosion proof pumps. And obviously, once you get into things like explosion proof, like metering or peristaltic pumps, that obviously begins to limit your availability with these types of systems. Here that you can see more like a heat trace style system here. This having to all be explosion proof as well. In a simplicity world, you can also use very simple technology. You can do things like hot boxes, which is a proprietary name, obviously, but very similar, just kind of basic outdoor pump boxes at that point, which allow you to basically give them the fundamental protection that they need, for like environmental treatment. So I've seen a lot of products at municipal plants, in different oil and gas rigs, for example, where they have done this before, where they basically had to put, these systems all over the facility. And they'll put things like this on there, which allows, for proper, environmental protection of this. I've just seen very bad results if you just put these systems outside, exposing if the chemical can be outside, the different gaskets, different pumps, the different pressure relief, back pressure valves. There's certainly can be issues when it comes to these types of systems, with their exposure to raw exposure to the elements. All right. So yeah, kind of leading back to the poll question there, and then we'll just kind of showing kind of the video of the different types of systems going on here. When doing a chemical feed, if you guys are approaching this, you have an application in your facility. There are, these are really the important things you need to look at, to allow you to properly design the chemicals, redundancy. These are really all of the above. You have to have kind of a complete understanding of what your system, what your system you're trying to build, the pumping technologies involved and everything else to allow you to properly design a chemical feed system. Chemical feed systems come in a lot of different types of configurations for applications, simplex, where, if you have downtime associated with the system, it's not that critical at that point. Duplex is probably the most common, whether it's redundant, whether it's a lead lag. And triplex, where you have an application where you absolutely cannot let a chemical feed or whichever type of system you're operating and actually shut down at that point. So when PID, it's kind of PNID level, this is a simplex system, it's a single pump operation. You see here you have your pulsation, you have your back pressure, calibration columns, you have your priming units. When you're talking about duplex, you can either have a shared, common discharge, or you can have or you can have separate if you want to have full redundancy at that point. This is more of a lead lag where you have I'm sorry, shared suction and discharge plumbing, whereas this one here is more of a true, you basically have a true duplex arrangement. And then finally triplex as well. Obviously you do share things like calibration columns and things like that, but otherwise every other pump basically has all of those different components that we discussed. That's all we really had for today, because I said before, we kind of wanted to do sort of a broad overview of, chemical feed and polymer feed. Obviously, this is a very diverse topic, and there's a lot of different applications out there. There's a lot of different chemicals. This is kind of the sort of the broad ideas of, how you activate polymers, where you're using them, the major components of chemical feed systems that delve into some of the pump technologies that go along with them. As well. As I mentioned, there will be a poll going out after this presentation. If you guys have any feedback, we're always happy to have that. We do have 2 other webinars scheduled this year. We'll have one on high purity water systems in early June, and then we'll have one on pH and hydrofluoric acid treatment sometime in the fall, most likely around October. Like I said, if you have any questions, we have some time now. If you think of any questions, afterwards, below is my contact information. You can feel free to reach out to me or the webinar organizers, and we would be more than happy to answer those offline as well.